In continuation of my lecture on quantum mechanics, today I like to present this lecture 2, Schrodinger time independent wave equation. It is the first stepping stone. To go into the quantum mechanics in details. Of course, quantum mechanics is highly mathematical, and so it requires some mathematics to know the details of this subject matter. In 1926, Schrodinger, while enjoying his holidays in a hill resort and doing ski on the ice, he was getting absent-minded. Then he came to his room and wrote a series of about 6 articles, out of which the Schrodinger wave equation, that is the first one. De Broglie suggested that the subatomic particles are also playing dual nature. Sometimes it behaves as particle, sometimes it behaves as wave. So electrons as a particle, whenever it is moving in an atom, confined to the periphery of this atom or molecule, this electron is also associated with this matter wave. And this matter wave is analogous to the standing wave. Just like the vibration of string tied between the two ends. As we have seen, the vibrating of the string tied at these two ends. The displacement of this string from this equilibrium position is measured by the amplitude function phi. And here the amplitude function is equal to 0. It is called node. It is also node. And between the two nodes, the middle point is antinode. It is antinode. X is the displacement of this standing wave. This wave cannot go beyond these 2 points, just like electrons cannot go beyond the periphery of this atom or molecules. The analytical expression of this standing wave is given by phi equal to a sine 2 pi x by lambda. Lambda is the wavelength. This is one wavelength. This is one wavelength. So A is some constant, or A can be taken as the maximum amplitude. Sometimes it is also called maximum amplitude function, and it is also called the sometimes amplitude. Phi is the amplitude function. Phi is the amplitude function, and this amplitude function is a function of x only in one dimension we are considering. The differentiation of this phi with respect to x twice, then we get a d2 phi divided by dx square equal to minus 4 pi square by lambda square into phi. This is an eigenvalue equation. Phi is the eigenfunction of this operator, d2 by dx square, and the minus 4 pi square by lambda square is the eigenvalue of this equation. Now the Schrodinger first considering the matter wave, this lambda is replaced by h by 2 pi, 2px. Px is the x component linear momentum. Actually, de Broglie's relations is highly appreciated by this all-time great scientist Arvid Einstein, and this appreciation also attracted the Schrodinger to take up or utilize this de Broglie equation. So this lambda is replaced by h by px in this equation, and phi, which is the amplitude function, this is replaced by the wave function psi. Phi and psi are having a different natures. Phi could be experimentally determined, it is a real quantity, but psi is a mathematical entity. It has no experimental bearing. So replacing this lambda and phi in this wave equation, classical wave differential wave equation, we get the d2 psi divided by dx square equal to minus 4 pi square px square by h square into psi. But instead of px, it is better to express in terms of this total energy E, and this E equal to kinetic energy plus a potential energy, and this one equal to px square by twice m plus v. V also be the potential energy, V is also time independent. As the force, the potential is coming from this force which is Coulombic in nature in the electron nucleus attractive forces. So this, as the Coulombic forces are time independent, so V is also here they are time independent. So px square from this equation we can write a twice m into E minus V, E the total energy. This equation, this replacing px square, here we get d2 psi divided by dx square equal to minus 4 pi square into twice m into E minus V divided by h square into psi into psi. But sometimes it is written that this h cross or h cut is equal to h by twice pi. This h cut is called a reduced Planck's constant. Reduced Planck's constant. Actually, in quantum mechanics, reduced Planck's constant. In quantum mechanics, in all almost in all relations, h and 2 pi are always associated. They are good friends. So instead of h, we can write h cross. When then equation is minus twice m divided by h cross square into E minus V into psi. Or coming to this left hand side, we get this Schrodinger equation d2 psi divided by dx square plus twice m by h cross square into E minus V into psi equal to 0. This is Schrodinger time dependent equation in one dimension. Time dependent and also the one dimensional Schrodinger equation. Whenever it is converted into 3D, then this equation is del 2 by del x square plus del 2 by del y square plus del 2 by del xs z square and psi equal to plus twice m by h cross square into e minus v into psi equal to 0. And the term within the bracket, here the psi is a function of x, y, z in 3 dimension. So this term within this bracket is replaced by the Laplacian operator. This one is del square psi plus twice m by h cross square into e minus v into psi equal to 0. This is called del square. This is called del square. Laplacian operator. So the Schrodinger equation construction, it is this psi, and if we know the potential energy of this system, then from this equation in one dimension, it is possible to find out the value of psi wave function. Wave function is a very important quantity of this substance of this system. If we know this psi, then we know all the informations of these systems, the total energy. So for different systems, we can now try to construct the Schrodinger equation in different quantum mechanical systems. Schrodinger equation in different quantum mechanical systems. Then first one is particle in 1D box, and it is like that. This is the box, and this is the particle of mass m. This is moving to and fro motions from 0 to L. X is varying from 0 to L, and the potential energy within this box is equal to 0, and outside the box is infinity. V equal to infinity, means very high. So in this case, the Schrodinger equation is d2 psi divided by dx square plus twice m by h cross square into e minus 0 into psi equal to 0, or d2 psi divided by dx square plus twice me divided by h cross square into psi. It is possible, easily it could be done to solve this double differential equations of this Schrodinger wave equation, and whenever we can solve this psi and e, both quantities could be calculated. Then second one, then in 3D box, this particle in 3D box, it is del square psi plus twice m by h cross square into e and psi equal to 0. Now we shall go for this second system. In case of second system, one-dimensional simple harmonic oscillator. In case of simple harmonic oscillator, we can write in different ways. Suppose this is this spring, and here is the metal ball of mass m, and it is vibrating. It is vibrating in this way, and if this is the x, and equilibrium position is xc, xc equilibrium position is xc, and x is changing sometimes because whenever it is coming compressed, x is less than xc, when it is elongated, when x is greater than xc. And for this equation, the potential energy for this system, as it is taken as the simple harmonic oscillation which obeys the Hooke's law, and the force is displacement is proportional, restoring force is proportional to x equal to k minus kx, and from this we can determine the potential equal to half kx square. K is the stretching constant, force stretching constant of this spring. So this equation in that case, d2 psi one dimensional dx square plus twice m divided by h cross square into e minus half k x square psi equal to 0. This vibration, we can consider the another vibration of this diatomic molecules. Vibration of this diatomic molecules. It is M1, it is M2, it is the center of mass. It is the center of mass, and this two bodies, two atoms are linked by this chemical bond, and they are vibrating, and it is called vibrational motions of this diatomic molecules. In this case, this equation will remain same, only this m is replaced by this reduced mass d2 psi divided by dx square plus twice mu divided by h cross square into e minus half k x square psi equal to 0. Here k is the force stretching constant of this chemical bond. And we know the higher the value of k, the more strong is the bond between these two atoms. Mu equal to m1 m2 divided by m1 plus m2. Now we are coming to this third system with the electron motion, or the motion of the electron in hydrogen atom. This is also very vital, and here is the nucleus containing one proton, and this is the electron. Suppose at this position, R1 positions, R position. R is the radial distance of this electron from this nucleus, and its x, y, z is the coordinate in Cartesian system, or in polar coordinate r, theta, phi. The motion of this electron in an atom, in this hydrogen atom, is 3D motions. And so the Schrodinger equation is del square psi plus twice m by h cross square into E. This potential energy of this electron of this electron is minus E square by R, and it is seen that this is time independent. So this becomes a plus E square by r into psi equal to 0. Here psi is a function of x, y, z. It is better if we consider the motion of this nucleus also, then it is better to replace this m by mu, the reduced mass of this hydrogen atom as a whole. Whenever we try to change in polar coordinates, it is better to solve this equation in terms of this polar coordinates. Means r theta phi. This del square becomes 1 by r square into del by del r into r square del by del r plus 1 by, this is the Laplacian operator in polar coordinates, r square sine theta and del by del theta into sine theta into del by del theta in plus 1 by r square sine square theta into del 2 by del phi square, and this is the expressions of this Laplacian operator in polar coordinates, plus twice m by h cross square into plus e square by r into psi equal to 0. R theta phi, r is the radial distance of this electron from this nucleus, theta is the zenith angle, and phi is the azimuthal angle. Now the fourth system is free axis rigid rotator. While the free axis rigid rotator, say we can write one this way, and this is the x-axis, this is y-axis, this is z-axis. One particle is moving on this xy plane along this x-axis. Here r is the radial distance or distance from this origin, and this is phi is only changing, theta is 90 degree always. Here r is fixed and theta equal to 90 degree, and this is also fixed. In Cartesian Schrodinger equation in Cartesian coordinate del 2 by del x square plus del 2 by del y square into psi plus twice m. M is the mass of this rigid rotator, h cross square into E minus 0. Here potential energy is 0, since this while this particle is rotating, the distance remains fixed, into psi equal to 0. Or we can write del 2 by del x square plus del 2 by del y square psi plus twice m by h cross square E into psi equal to 0. In polar coordinates, in Schrodinger equation in polar coordinates, or in terms of this r theta phi, r is fixed, so this term will vanish, and theta also fixed, so this term will also vanish. Here the theta 90 degrees sin theta equal to 1, sin square theta also 1. So this term only is left, 1 by r square into d2 psi by d phi square. This is no longer partial derivatives, it is only one variables are there, plus twice m by h cross square into e and psi equal to 0. If we change, we know that mu m r square equal to moment of inertia, moment of inertia of this rotator, moment of inertia. So r square, if we multiply by r square, then it becomes d2 psi by dx square d phi square plus twice m r square into e divided by h cross square into psi equal to 0, and m r square we can write I. So Schrodinger equation in case of rigid rotator becomes d2 psi divided by d phi square, psi is a function of phi, plus twice I e divided by h cross square into psi equal to 0. So the last one, this last system we can consider here, the helium atom, electronic motions of this electron, motion of the electrons, two electrons are there in helium atom. Here at this nucleus, two protons are there containing the two positive charges, two positive electronic charges. Here is one electron, say E1 at this distance R1, and here another electron E2 whose distance is R2, and this one, between the distance between these two electrons are 1, 2. The potential energy of this system is minus 2 e square by r1 minus 2 e square by r2 plus e square by r12. This to this one, from this to this one, and these two is like this. So potential, so the Schrodinger equation is then del 1 square for these coordinates plus del 2 square into psi plus mu twice mu divided by h cross square, and this should be written as mu for this case of hydrogen atom also better, though mu is almost analogous or almost very close to this electron mass. And here E and plus twice e square by r1 plus twice e square by r2 minus e square by r12 and psi equal to 0. Here psi is a function of three-dimensional x1. This coordinate is x1, y1, z1, and this coordinate is x2, y2 and z2. So this Laplacian operator psi1 square equal to del 2 by del x1 square plus del 2 by del y1 square plus del 2 by del z1 square. Similarly, Laplacian operator for the second electron is del 2 by del x2 square plus del 2 by del y2 square plus del 2 by del z2 square. For the system containing n particles, last one, for the system containing the n particles, for system containing n particles, this Schrodinger equation is summation of 1 by mi, mass of each particle, into del I square plus twice 2 by h cross square into E minus V psi equal to equal to 0. This is all about the formulation of the Schrodinger equation, time independent wave equation, and its construction in different quantum mechanical systems. Thanks again to you all, and if you like this video lecture, then please subscribe.